folks have There's now a great deal more interest in exoplanet science around the Midwest. We've had, of course, our own giant Dong joining here, but there's been several recent exoplanet hires around the area. One of the most recent is, of course, Cristobal Petrovich, who is effectively right next door at Indiana University in Bloomington. It's a lovely, lovely campus. Before he joined there, Cristobal did his doctoral work at Princeton before moving to Canada as a CETA and a Global Fellow, and then moved to Stewart Observatory in Tucson, Arizona as the Patrick Bach Fellow, and then started a faculty position at Católica in Chile, where he was until 2023.
And 2024, last year.
2024.
So very recent.
And then moved to Indiana, where he's joining Sangwoo Uzu to create one of the other expert research nexus in the area. Today he's going to tell us about his work on orbital resonances and exoplanet systems. So Cristobal, please take away that.
Thank you, Gautam. Thank you for having me here. I had very nice interactions this morning with many of you. And today I want to present what I think is a new picture that is becoming to focus of how planetary systems evolve as a whole. And this is really thinking about the resonance structure of exoplanets and how they dissolve over time. And those may be the chaotic life cycles of exoplanets in general that we see in the galaxy. And this is work that I done with here the students, 2 grad students at IU, one student at Católica, we just finished, and 2 posters, one in Chile and one at IU. So this is the picture that we had previous to 1995. This is 7-meter axis, or orbital separation of planet mass. You have the solar system planets. And as you may know, in 1995, the first exoplanet around a sequence star was discovered. This is 51 Pegasi b, discovered by Michel Mayor and Didier Queloz. And it's this point over here. So this really opened the era of exoplanet science. And this particular case is what we call a hot Jupiter. So a planet that has a Jupiter size, Jovian size, in between Jupiter and Saturn, but it has an orbital period of about 5 days. And it was actually the first exoplanet puzzle, how these hot Jupiters form. How do you get that amount of mass in this very confined region of a protoplanetary disk, for instance? How do you get the solids to actually form a planet that big as such a small orbital distance? And one of the things that is being invoked many times is orbital migration. It's going to be one of the driving themes throughout this talk too. We had more radio velocity planets being discovered. This is from the Exoplanet Archive, just pulled out a couple of days ago. And already the baseline expands almost like 3 decades in many of the systems. We now know that these hot Jupiters are rare. They orbit about 1% of sun-like stars. And the majority are actually like our own Jupiter, what we call cold Jupiters, in about 10% of sun-like stars. We still don't know what the answer is to the origin of hot Jupiters, and that's still a highly debated. It's the longest standing puzzle in exoplanet science. Transit surveys discovered all these planets and started populating different regions of phase space. We started from the ground, detecting many of these hot Jupiters again, but really the revolution came from actually getting extreme photometry from space, in particular from Kepler, detecting this class of planets that are called super Earths or sub-Neptunes. All this region here, it's hard to detect planets because of selection biases. We're lacking the precision or the baseline to detect planets there. But what we have already, we can already see, for instance, if you do the demographics and the statistics of all these planets that we detect here by the transit surveys. And there are many works on this, trying to get what is the number of planets in this region, what is the frequency, and the size distribution, and just highlighting a work that we did at CETA, where it gives you a picture of how many planets are per star and what is the typical demographic. So we have to think of 3 planets inside the orbit of Mercury, roughly, that have roughly 5 Earth masses. And the currency is about 30% of stars. So multi-planet systems, compact, inside the orbit of Mercury, 10 to 20 Earth masses total. So still the question of mass appears, the same as the hot Jupiters to some extent. How do you get all of this mass? And migration is invoked in many cases too. Other campaigns have populated different parts of phase space. We have the direct imaging planets. These are very wide orbit planets, self-luminous, so around young stars, very massive. We have the planets now populating here through microlensing campaigns from the ground. And we'll come back to this at the end with Roman, which is an exciting mission that will probably discover many of these planets in this region. But just for reference, microlensing is really populating the region, so between 1 to 10 astronomical units, right? And it's fairly independent on the mass scale because it actually scales as the square root of the mass. So the goal of my research, and many colleagues in the field, is take this plot and use the demographics to infer how planets form in general. Right? To construct, not only use mass and semi-mirror axis, but also use planetary radii, planetary eccentricities, stellar obliquities, and so on. Anything on multiplicities, speed ratios, all the information we can actually back up. So that's the goal, and that's what we try to do in my group. And one of the questions when you try to address that, how to populate this, is how you evolve things in this axis, the orbital separation, semi-major axis. And a big bottleneck to our theories comes from orbital migration. So the question is, the question of planet migration, I would claim, is a fundamental and solved problem in our theories of planet formation. We have a theory already that is about 40-something years old, where you stick a planet in a protoplanetary disk. This is just an image from a 2D simulation from this review. It launches spiral density waves that you can see here as over densities. These waves carry angular momentum and energy. And as a back reaction, so depending on how much angular momentum is carried inwards versus outwards, if there is a difference between these, you have a torque, and the planet migrates to conserve angular momentum. Most models predict that the time scale for migration is inwards and it's very short. So the problem then, of course, there are many solutions to this, and people have been working on this, is because this driven migration is so rapid, planets would either fall into the star or accumulate at the disk inner edge, failing to reproduce the observations that I just showed you. That would be a somewhat provocative statement, but that's what the theory in itself would predict. There are ways, of course, to actually get the planets to part, reverse the migration. They involve detailed thermodynamics, or the role of multi-planets that actually can reverse the migration. But this is still kind of a bottleneck of our theories of how to populate the landscape of exoplanets. And just to illustrate how this looks with an actual formation scenarios, and taking the example of Jupiter's, the models span from a wide range. From the canonical picture, you start growing a core until it reaches a critical mass, and this is how they taught us how Jupiter formed. It starts accreting an envelope, the envelope becomes massive enough, you undergo runaway accretion, and after that, you can undergo orbital migration to form a hot Jupiter. That's been one of the solutions to explain hot Jupiters. There is a debate of how planets orbit, if they orbit through this planic interaction, or they do it dynamically by something termed high eccentricity migration. I will not get to that. And on the other extreme, planets could potentially form, and this is being proposed after the Kepler planets were discovered. I told you that there is already significant amount of mass in these regions, about 15, 20 Earth masses. So if these cores actually form quickly, and they have envelopes, so they probably do form relatively quickly when the disk was present, if you just get collisions between these bodies, they can actually accrete or become a large enough core that can trigger runaway accretion. And this is being proposed by a number of authors. So these are the two extreme cases. As you might imagine, comparing the nature of planets forming in this way and this way would be totally different. So people try to tackle this question of using composition studies. For instance, atmospheric composition by spectroscopy, planets that are born very far from, say, the ice line. Any of the ice lines may accrete different amount of material. Therefore, the composition should be different. And people have discussed these carbon to oxygen ratios, for instance, which would be totally different compared to systems that are actually formed in situ. That's one way. People have also discussed doing forward modeling by carrying out these population synthesis models. And what I do in my group is use the architectures and orbital architectures to back out, in particular, the question of this talk is about migration. Can you use and infer with the current demographics that planets have engaged in migration, how long of a range the migration was, if there was any, and help improve any of these models that people have worked on. Luckily, for a dynamicist like myself, you don't form just a single planet, but you form several. So this would be a track of 3 Jupiters. And in particular, if you plug them in your favorite hydrocode and let them evolve, you see now we have 3 planets here. They undergo sometimes convergent migration. They approach each other. And when that happens, they can be locked into what is called MMR, mean motion resonance. So the dashed lines here is in this plot. So this is time 7-meter axis. The orbits are decaying. The dashed lines show the regions where the orbits are commensurate in a 2-to-1. So the Petrovich ratios are in the 2-to-1 ratio. So they get locked and would evolve this way. And this would be the smoking gun of orbital migration. And this has been predicted for a while. In fact, we know this even in the sort of, yes.
Yeah, so for triple planets, it's like the resonant chain where only the innermost pair resonates.
Right. So in the case that I show here, this is cherry picking. This is actually a Laplace resonant chain.
Okay.
So all 3 planets are in that, yeah. And that was exactly what I was going to explain now. So to give you sort of a sense of resonances. The best example and the easiest quote unquote to understand is the Laplace resonant chain that he noticed for the Galilean moons. So if you have Io, Europa, and Ganymede, the Peter ratios go in the 1 to 2 to 4. Exact. He noticed that. And that's a very stable configuration. And it's actually the product of the migration of the moons. So like our own moon is receding from us. The moons around Jupiter are receding from Jupiter. They're causing tides on Jupiter. They migrate out and they get locked into this Laplace resonant chain. It's right here. And it's not a statement about the commensurability only. It's also like the angular phases are synchronized such that you get into this equilibrium state. So this is trying to illustrate this with this cartoon. So this is actually some t equals 0, 1 orbital period of Io, the innermost, 2, 3, 4. After 4, it repeats again. Yes.
So how do we know that this is a result of the tidal interaction and not the formation process, just like the moons?
Because we see the moons migrating down too. They're still drifting apart, and it's the same case for Saturn moons. When you do astrometry, you see that the moons are actually moving a little.
But the fact that they're moving now doesn't mean that.
Right. Yeah. They go. Yeah. I don't know. You could have a circumplanetary disk that maybe lock the moons in resonances, meaning formation. It is possible. Yeah. The one thing that people do is to assume, because we see the moons moving now, that if they started at the Roche limit, very close to Jupiter, you can back out what is the amount of tidal dissipation you get in Jupiter. And it gives you like a reasonable number compared to sort of like things you get in exoplanets. Yeah. But yeah, I'm not sure if people discuss formation as a scenario, but it may be possible. It's the same dysplanic interaction, just with a circumplanetary disk. But the configuration you get is this one, where never you can have here I'm indicating conjunctions. You never have a triple conjunction. right? So if we are doing like one period, this is always coming back to the same point. This is half, half, the red, half, half, and then it repeats again. So you can see that this is a very stable configuration because you never have three planets having a conjunction at the same time. And this is actually what it's the Laplace resonances in a toy model. I'm introducing this because I'm going to use it for protoplanetary source. The other example that we know and love is Neptune. So Neptune captured Pluto in the 3-2 resonance, the orbits cross. And the only reason why Pluto survives is because the planet Neptune and Pluto are in a 3-2 resonance that avoids these conjunctions again. And that's the reason why we know that Pluto actually migrated outwards due to planetesimal trivial interactions. We observe resonances around the early image planets. I'm just gonna give you a tour of the exoplanets that I think are kind of like the coolest on this. The first one is PDS 70, which is, you see the protoplanetary disk. This is a composite image. This is the first image that you have actually two directly imaged planets, PDS 70b and C, with astrometry that claims to be at least close to 2-to-1 resonance, but it's not totally clear. And then we have HR 8799, the first multi-planet system that was detected by direct imaging. It has 4 planets, claimed to be in the 8-to-4 to 2-to-1 mean-motion resonance, or Laplace resonance, which is kind of striking. If you go to shorter orbital periods, you have famous examples, like TRAPPIST-1. It has 7 planets. It's actually so compact. Look at the scale here. So we're really talking about 5% of an astronomical unit. And this is because the star is so tiny that actually there are 3 planets that are in the habitable zone that is right about like 2% of astronomical unit. So it's a tiny compact system. It's so compact that if you were to just run from the discovery paper in 2017 and put it in your laptop and run an embody, it will become unstable very quickly, unless you put the planets in resonance. So we published a paper on that in 2017, taking the posteriors from the detection of TRAPPIST-1, and it only is stable if it is in resonance. And in a very high dimensional space, if you're shooting darts, that's almost impossible to get. Like it has almost zero measure, if you like. So it's a very, very hard. So it has to be extremely fine-tuned. Therefore, migration dissipation had to happen in the system. We have other systems that are appearing lately. TOI 1136 with 6 planets in a resonant chain. Now the scale is slightly different, a little bigger. And HD 110067, again with 6 planets in these complex resonant chains. And there are many other examples. But the problem is that most exoplanet systems don't look like this. So if you want to really push the idea of, yeah, planets are born in resonances, something else has to happen. And in particular, we think that dynamical instabilities are actually shaping planetary systems. So erasing some of these underlying resonance structure that could inform the migration history. So the idea is that we start with systems like this, very dynamically cold. This is the edge top view. They get unstable. You lose planets to ejections and collisions between them. There is widening of the orbits. They get dynamically hotter until you get to the present time where you lost many planets and the orbits became even more dynamically hot. In order to understand how this plays out in this diagram, we have to define one quantity, which is called the Safronov number or parameter, which is the ratio of the escape velocity of the planet to the Keplernian speed. It really defines what outcomes you get from this instability, whether you get ejections or whether you get collisions between planets, right? Roughly like the branching ratios. I'm showing here the black line, which is unity here. If you're in this part of parameter space, where Jupiter is, Jupiter scatters everything out. It's the big ejector of the solar system. So if you get Jupiters getting unstable, you mostly get ejections. Planets are being ejected from the solar system. The ones that survive end up in very eccentric orbits. And that's been already a model that's been very successful to reproduce the eccentricities of cold Jupiters. So this is how we know the instabilities actually played a role here. The orbits of cold Jupiters are fairly eccentric. On this other side of the diagram, we have mostly planet collisions. That's why Earth actually gets hit and cannot really scatter minor bodies, right? So we're actually living some here below this ones. So in this case, you mostly get planet collisions. And the reason why we think that these planets have been shaped by instabilities is because of statistics coming from Kepler that you can actually model the underlying multiplicity and the RMX eccentricities and inclinations. The less planets you get, the dynamically hotter the system looks. This is an observation from Kepler. There's another line of reasoning that comes from the fact that planets seems to be accumulating close to the dynamical stability limit nowadays. They're very tightly packed. So maybe in another decade, say in 10 billion years, they could become unstable again. And this repeats over and over. It's like planet formation is never over in some sense.
Quick question. So if you go back to the previous slide, looking at either side of the Safronov number cutoff there, the mass is also quite different, right? Like the ejections tend to be at much higher masses than the ones that are collisions. Is that just an observational effect, or should we actually assert that there's going to be some range in which you don't really get very many planets forming, some range of mass over which you just don't get planets forming?
Right. Sorry. This parameter is depends linearly with the mass. So, right. So it's about some threshold as you go up in this axis.
So you basically
right. So here, if there is an instability, it actually sets very quickly.
Mhm.
You eject stuff, and that's it. That's the end of the game. Here, you can go and I show like these 7 planets all together. You can have an instability, decrease the number by say 2, and this can sort of like continue until you deplete the system. And that's because indeed they get collisions, so they're more forgiving, if you like, to cause like a global instability. Just neighbor to neighbors collide. Yeah, that's a very good question. Yeah, this is a bit of a long introduction because I know that the audience may not be extremely familiar, but you will with DJ, I'm sure.
Yeah, I have, so in terms of the Safran number, we try to explain the whole map in terms of Pamba scattering. And in that case, like, do we really care about whether they're in resonance or not in resonance? Because as long as places close enough, they can always get the scattering.
I think so. No, I don't think it does.
Okay, so
Yeah.
the resonance pictures just totally wash out when they.
Exactly. I will get to that. Exactly. That's a very good point. Yes. Yeah, it doesn't really care. Actually, like if you think about Jupiters, all these scattering experiments people practiced in the past, they started with very agnostic initial conditions, and they just get this sort of like a Rayleigh distribution, regardless.
Right, but as you said, it's like through the dart, you need really precise configuration. So in this simulations, they don't really cover like in mean motion resonance setup. If we do begin with that as the initial condition of the simulation.
There are a few words that have look into
yeah.
this, and they get the same, so it's watch out.
Okay,
Yeah, that's a good point. Okay, so to summarize, models predict that resonance should be common. There are some examples, but most exoplanets seem to be shaped by dynamical instability raised in this primordial resonance structure. So the question that really motivates recently my group is, were resonance prevalent early on and then disrupted, or they were not common at all? So we'll discuss 2 venues from a group. This is hydrodynamic simulation. These are embodied simulations, what we do. The first part will I showed you an example of a system that we think we're catching the planets in this migration journey very early on using ALMA images, addressing this question. And in the second part, I will try to disrupt the resonances, and I will show you how. So this is an image of HL Tau that you might have seen from 2015. Planets that interact with the gaseous disk, they carry, the waves carry mass too, so they start depleting the regions around their orbits. So they carve these gaps. People since then have been attributing this to this pranic interaction. There are other alternatives, of course. There was a recent paper showing a planet in one of these gaps, actually very recently, directly imaged. So it seems to be that in some cases this is the case. So if you were to just draw ellipses here, and people have done that, they realize that maybe the systems are actually maybe give you information about possible resonances forming early on. And in fact, some colleagues argue that if you populate this range, the only way to get it stable, even though the system is very young, is for the system to be in resonance, very similar to like the Galilean moons. We're trying to do something a little bit beyond that, just placing planets. We're looking for non-axisymmetric structures inside the gaps. And in particular, we're looking at possible accumulation of material inside the gaps around the stable Lagrange points, L4 or L5. And this is really motivated by this system PDS-70 that found, like, I'm not sure if you can see it here, but about like 60 degrees away, there is this clamp over here of dust, and this is the directly imaged planet. So this is in the trailing. We know the rotation of the disk, so we know this is the L5 trailing Lagrange point. There's another system, LKCA, that if you subtract the axisymmetric, you just take rings and take the residuals, you see very prominent L4 accumulation of dust, and maybe a clamp here on L4. There is no planet, but you know that this separation between these two is 60 plus 60, so consistent with being Lagrange points. So my student, Agustin, has been looking into this and whether you can produce these structures and whether you can break the symmetry between the Lagrange points, because I will show you one example, but we only see it in one, in the most prominent case that we'll show you in a second. So he's carrying out hydrodynamic simulations, and this is just showing what you get for the gas around the rotation. So the planet is here. This is in the vicinity of the, you see that there is a gap here, and you see the streamline. And in a nutshell, we're finding that this is actually fairly robust. You can accumulate gas here and start trapping dust that it would be observable in, say, 1,000 to 10,000 orbits. So it's very long-lived to actually be observable in ALMA. And the one parameter regulating the asymmetry between L5 and L4 is the temperature gradient. So if the temperature actually decays with orbital distance, you should see material just in L5. And this is actually a very robust result from the simulations. So this could partially explain, for instance, that L5 in this image is larger than L4. Okay, so this is another example, HD 163296. You clearly see the gaps and rings, and you see like this crescent very marked. And this is only just a single crescent. If the theory is correct, this would correspond to the material of a Lagrange point of a planet that we don't see. It's probably enshrouded in dust. We can actually zoom in this region. This is actually a very prominent structure. But it's not at the center of the gap. So we posit that there are actually two planets in this system. And then you can try to provide with a global model and see if we reproduce the image that we see from ALMA. So let me show you what we get. So this is the ALMA band 6. These are simulations done by Juan Garrido at Católica. This is a synthetic observation. We're modeling the dust here too. You see that the crescent is nicely reproduced. The gap here, and then the rings, because we added more planets. And that's actually not the hard part. The really hard part is to get this part right. And you see that it doesn't look totally symmetric. It's off-center from the gap itself. So we're saying that there are two planets actually there at the 4-to-3 resonance. And that allows you to actually do some cuts and see the radial profile. It actually reproduces the position of the crescent, the rings. You can even do better. There is a CO emission from the disk, and you can see the gas gap that it roughly coincides with the with our solution, which is like having two samples. So the previous solution was a single Jupiter. The gap itself is very shallow. So we have a model where we have 4 planets. All these planets outside, if you just throw ellipses, they actually fall into a 1 to 2 to 4. You see, it's actually fairly symmetric, and you can actually do that just from the image itself and apply Kepler thermal. Yes.
So sorry to interrupt, but could you please close the banner that says not clearing? Sorry about that.
No worries. Thank
so
you.
much.
Yeah. Yeah, it was indeed blocking. It's, this is blocking.
I think there's also the talking banner.
How?
More, I
Just move it to the thing.
Ah, yeah. Oh, it's still,
It's.
No, it's just okay, yeah. Right, you couldn't see the titles. So we provided a global solution where we have the other planets actually in a Laplace resonance. And we can do even better than that because we have the information of the gas profile. So our best solution that reproduces the gas and the dust, we can just run it in an embody, prescribe the migration rates that we get from the profile itself, and see if they actually engage into the resonance, if there is convergent migration. And that's exactly what we did. And we have the information about the scale height of the disk and so on. So this is the semi-mirror axis. The planets migrate the star away from the 2 to 1 resonance. They get locked into the 2 to 1. And the 2 inner planets are close to the 4 to 3 and it gets locked with very small eccentricities. Okay, but we can do even better than that because I told you about the phases, and being in resonance is really the orbital phases following a relation, right? Like the Galilean moons. So the 3-body resonant angle, which is this set of angles that we care about, is very well constrained from the dynamics. You can convert that to positional angles. They're not exactly the same because the orbits are slightly eccentric. And you can start relating the positional angles of 3 planets following this relation, for instance. So we know that planet 2 has to be 60 degrees away because it's the L5 that is present. Previously, there was a planet claimed to be here by velocity perturbations to the gas, what they call velocity kinks. We can use the relation and say where the planet 1 is. At the same time, we submitted the paper, we sent it to Astrophysical Journal Letters. It was this paper that appeared on the archive. So it was kind of like a prediction, post-diction. And they claimed that there was a planet exactly where we predicted the planet 1 was. And this is by looking at the C1 emission. And even more recently than that, the JWST NIRCam also spotted a planet at the same location where the planet 1 is. So maybe there is some truth to this, or at least we're making a prediction. And this is something that people haven't really used in the past. These resonances in disk to give you extra information about the gas and dust dynamics. Good. So are the resonances assembled when the disk is present? Can we catch the planets in the migration journeys? HD 163296, I think, is an example. Is one of the best studied disks, and I'm sure there's going to be more data coming in. Maybe locating the planets and see if this migration history holds. But it's the first potential Laplace resonance just using these images. Okay, so in the second part,
Sorry, 4:20, you have time.
what is the time?
It's like 4:20.
But how much time is
Yeah.
35? No.
25,
Yeah.
Okay, yeah.
Can I ask another?
Yeah, sure. Okay, yeah, so that's possible.
See today in this department. Correct.
They're not synchronized, there are no resonances here.
Yeah.
Sorry.
Yeah, so for all the Trojans we find, is it always like 60-degree away?
Yeah,
Okay. But like from the dynamic perspective, we know like different resonance orders, the Trojans should be at slightly different locations.
the Trojans,
Yeah.
like Jupiter Trojans.
Yeah, exactly.
Yeah, and the symmetry is different. You have more
Yeah.
L4 than L5.
Right.
Yeah, there is a second aspect to this.
Yeah.
Is that and that's what we thought initially. Maybe this is not like gradients of the temperature of the disk. It's just the migration itself
Yeah.
creates an asymmetry, and that can be studied like even analytically.
Okay.
In order to get L4 being more prominent than L5, I think it's outward migration
Okay.
or so. Yeah, I have to remember, but it's of course, one of the two. But yeah. So we're actually studying that, trying to now put migration in the models and see, because then you need to model the task. So if it was just particles that don't feel any drag, they're just affected by the gravity. Therefore, they would just follow the same as the Trojans. If they're very coupled, they follow the temperature gradient. So there has to be a range that is actually becomes symmetric when you have migration and the temperature gradient. We're
Right.
exactly looking at that.
Yeah, and for the hydro simulations, you just add some precipitation on the temperature gradient. There's no
Yeah.
like cooling.
No, yes, yeah. It's a very sort of a controlled set of experiments. So how do resonance break? That's better, I hope. So for some of the wide orbit planets like HR 8799, these directly image planets, you might invoke stellar flybys. And that's one of the works that my postdoc has been carrying out at Carolina Charlambos. In a nutshell, if the flyby counts about like 3 times the size of the system, and the 2 to 1, they just break up. But this cross section is relatively small. It can be much bigger for the 3 to 2 results. But the real question is what happens for short period planets, most of these Kepler planets. And this is a recent paper by Fei Dai showing the incidence of resonances as a function of time. This is kind of like a heterogeneous sample, but you get that it's roughly order unity with big error bars for planetary systems around stars that are younger, roughly than 100 million years, and then it starts decaying. These error bars here are very small because we have many planets on this side. But this one is composed of like 7 or 8 planetary systems. But if this picture is true, the question for a dynamicist is how do resonance break in a timescale of 100 million years? It's kind of a weird timescale because the disk lives for million to 10 million years. So why you get this jump from here to here? In terms of orbital timescales, this is about like a 10 to the 9, 10 to the 10 orbits. So unless all the systems decide to sort of like chaotically diffuse and become unstable in those timescales, sounds a little bit fine-tuned.
It's kind of a orbital rotation time scale of the galaxy, right?
That too, yes. So there could be a layer of dark matter. Yeah, no, but these orbits are tiny. So you have to think about like 0.1 astronomical unit. So it's actually causing there any upheaval. I think it's mostly disconnected from the galaxy. Yeah. So people have invoked mass loss from the planets, overpacking, A2. What my student has been doing is to look at the same history of Neptune, because we know that Neptune migrated, captured Pluto in the 3 to 2 resonance in a timescale that is comparable to this 100 million year timescale. So we're invoking cold Neptunes here. We have the transiting chain, we have a range of cold Neptunes that we haven't been able to detect yet because of selection biases. But if these are in resonance, kind of makes sense that everything is kind of in resonance. There's debris after planet formation, and we'll see the dynamics from that. So this is really motivated by the migration of Neptune in the solar system that happen in these timescales. We know that cold Neptunes are very common from microlensing campaigns. They're 10 times more common than cold Jupiters, for instance, also from radial velocity. And also there are many free floating planets that have been discovered having masses of connectors. So somehow you need to be ejecting some of these connectors. And these really live in Saffron of number of unity, right? So people have worked out the dynamics here, but here it's kind of like a less clean problem because you have mixed outcomes. So let me show you a set of snapshots from the simulations using a rebound. We have the orbits here in thick lines. So these are 5 Neptunes. We have 1 Earth mass in 30 embryos. So these planetesimals, which are the thin lines. This is after 1,000 years. This is after 10 to the 5 years. You start scattering some of these minor objects. This starts getting thicker. These are the different projections. This equilibrium that I talk about the resonance, they start being washing out after 10 to the 5 years. So you kick it out of the resonance. The number of planetesimals start decreasing in timescales of 10 to the 7, 10 to the 8 years. You just kick them out of the planetary system. They're lost to ejections or collision with the planets. Now it's all a mess. It's very thick. And they start transferring angular momentum to the orbits. So there's this quantity that we call the angular momentum deficit, which is a way of summarizing how eccentric or dynamically hard the orbits are, eccentric and inclined. And they start actually growing in time. And they keep growing until you have a close encounter between the orbits. So it's 2 ellipses encountering this point. And then chaos becomes global. Start shooting up all of the planetesimals outside 70 million years, 100 million years. And we can repeat this for 120 or so simulations. And I start looking at the outcomes from that. We find that about 2 planets remain bound. There is a equipartition between ejected and tidally disrupted. This number is actually very high, like 70%. So about 0.7 per star. Yes.
So you're making a prediction about the population of rogue planets, right? So
Exactly. Yes. That's what I'm going after. Yes. And you see the mixed outcome. So the number of collisions to the sum of ejected and disrupted is roughly the same order. And this is exactly because the Saffron number is of the unity.
In all of these sims, so 100 million years, you're maybe not worrying about the dust disk around the star itself. But at 10 to the 5 years, I imagine there's still some amount of that dust left, and it must be interacting with the star itself. Do you have to treat the star as essentially being static in these sims, or?
Yes. So I didn't show it, but we model everything from the migration of the planets into resonances, then get rid of the disk, and then start like the planetesimals affecting. Because initially they're just mostly affected by the gas disk. We do these sort of transitions, but I'm just showing the fun part. We have to place the planets in resonance. Yeah. So we get, this is the stabilization timescale. We want it to be close to 10 to the 8 years. Different masses of planetesimals and planets. As you get less planetesimals, it gets longer, as expected. And roughly the number we're getting is 1%. So you need a planetesimal disk that is just 1% of the mass in planets. That's not too big. In particular, if you think that in order to migrate Neptune, you needed something in the order of 10 Earth masses, even 20, right? So, and some of the systems, this is the typical evolution of one of the systems. You see this, the semi-mirror axis and pericenter distance. In some of the cases, the planets actually approach very close to the inner regions. And this is where the Kepler planets live. So if they become unstable, they're gonna cause an instability in the inner planets. In fact, if you just take the minimum pericenter distance, you get about like 70% of the cases, you get a planet getting as close as 0.1 astronomical units. This is 20 solar radiae. And Kepler planets live around this region. We're experimenting with now adding the Kepler planets, and this becomes really expensive. Because now we have to treat orbital timescales of about a few days. Right? So this is with one of the resonance systems, and we have gotten up to like 1 million years But you can see that these Neptunes actually cause the disruption of these planets. So we're still working on that and thinking about a smart way of modeling this, maybe with a mixed model of a secular sort of a dynamics and body. Okay, so if resonance are prevalent, how are these disrupted? Our proposal is planetesimal disk of Neptunes. And this is an area that has been very unexplored. So there are many things that can actually happen. I show you that there are many tidal disruptions. So if there are any predictions from this model, either many of the planets would be tidally captured, something that we term as high eccentricity migration. Some of the planets been very close to the host star. When they come at pericenter, they get sort of stretch. They relax at apocenter, they come back. There's tidal dissipation, you drain orbital energy. And when they get tidally captured, like the history of hot Jupiters that people have explored in the past, it can happen to the same to Neptunes, and they end up in these polar orbits, highly inclined relative to the equator of the star. My student, Juan Ignacio, has been carrying this investigation on using espresso spectrograph in Chile, trying to measure with the Rossiter-McLaughlin effect the orientations of Neptunes. And something very surprising actually happens for hot Neptunes, is that these are the projectile stellar liquid dips, that there seems to be a population of polar Neptunes. In fact, you can do the Bayesian analysis with the population we have. These are the cosine of this angle, so this would be polar, this would be a line. Juan Ignacio has been actually using the Bayesian framework that it was developed by DJ to create these curves. And indeed, depending on the priors, you actually get distributions that are tantalizing as these polar Neptunes, which is one of the predictions. This is still to be done. We're still running the campaign. This is expensive. You need time in espresso in many cases, which is very hard to get. Okay, so Neptunes, they start here, suffer no number over the unity. Some of them may actually become hot Neptunes. Some of them free-floating planets. Roman is coming up online. We can start taking branching ratios. So how many of these you predict to be hot Neptunes in polar orbits? How many stay bound in the region that Roman can actually find planets? And how many of those are actually free-floating? So we're excited with the prospects of studying Neptunes. And if there's one message that I wanted to convey is that this picture is coming into focus. So we think that systems may actually get in these resonances early on. I showed the example with this disk, but there are many other arguments. There is a phase of a dynamic instability that can give you any of these results. The question is, what is actually driving instability? Our proposal is planetesimal disk, but the question is still up in the air. But finish here and take any questions. Thank you.
Can we have time for questions, Charles?
Yeah, you should apply from the Dye et al. Paper, which was fraction of systems in resonance versus time. And I'm wondering if it's possible to sort of misspin things here, like how close do they have to be to resonance to be counted as in resonance?
Yeah.
And if they're not in resonance, then they could just wander away, right?
Yeah, so some of these first order are like actually near resonance. The one thing they do though is to apply the same criterion for all of these beams. The question of whether some systems are in resonance or not is very hard to determine. Yeah. There are, and we really care about this beam over here because there are only 7 systems here. But there are a couple of systems there that are in resonant chains that are actually confirmed resonant chains. The other could be near commensurabilities, say within 10% of a commensurability. Yes, but this is still very recent. So we need to, there has to be another group also looking into this to complete the picture. But yeah, this is mostly becoming possible now with surveys like TESS and looking at young systems that it wasn't really possible with Kepler. So very excited. Hopefully we'll have more data points in this part. That's a good point.
Questions?
Brian Fields has a question online.
Right?
Yeah, Cristobal, thanks for your wonderful talk. So I was thinking about Oumuamua and the other sort of interstellar objects. I mean, obviously they're aliens, but if we relax that assumption, could those be ejected planetesimals?
Yes. Yeah, presumably, so there is a size distribution of stuff in the galaxy. You have more planets free floating than there are stars. You have many more minor objects like planetesimals just going around. We'll probably get the correct sort of a number, quote unquote, with a LSST. So far, there's been only 3 interstellar. But the one thing about Oumuamua is just the aspect ratio is so weird that yeah, I'm not gonna comment on the alien.
Thanks.
But yeah, these are planetesimals, and I think one of the most compelling explanations was that it's maybe like a fragment of a Mercury-like object. So it's very easy to sort of eject stuff from those regions, and it's not a comet. Yeah, I can share my favorite proposal by email.
Cool, thanks.
No, I mean, actually, on that point, you showed us sort of an expectation value for the number of things that were ejected of like 0.75. And, looking at the hundreds of planetary systems that you have, you'd say 3 things that are interstellar compared with fraction of 0.75 with 5 Neptune seems inconsistently low.
Oh yeah. Yes. So this number is actually falling short. In fact, at this point, maybe I went too quickly through that. But the number that we have from the current microlensing estimates is 1 to 5 roughly for the Neptune size. So more free floating.
We should expect more.
Yes. And that's exactly what we want to calibrate. If you have Jupiters being the ones ejecting, then you run into another problem is that we don't have enough Jupiters to do this. Neptunes is probably enough, but Neptunes are not great at ejecting unless you start with more, or if you start closer to where Neptune is, where the Saturn number is larger, and you start ejecting. So you can always move these, but we're trying to explore this region because it's the one amenable for Roman. This goes beyond what microlensing campaigns can actually probe.
And since you mentioned LSST, is that there's no reason one should expect this to be in the plane of the ecliptic, right? These can scatter in any direction.
Yeah.
Paul?
I mean, based on this, what would be the expectation time for how long we should wait until we see a road to start to interact with our solar? So,
Oh. I haven't done that. Yeah,
I mean,
a very long time, but
we have to wait a very long time, longer than the age of the universe for a star to do that.
Oh.
But if there are more of these than stars, then presumably, our chances are better, right?
yeah. I don't have a number in my head. Yeah. But I mean, the one advantage is that you could detect them out to say 100 U, right?
Yeah.
Give or take. So yeah, the question is, what is I guess it's like a cross-section kind of thing.
Exactly.
But we still don't have the number of free-floating planets of Neptunes really pinned down. We have like order of magnitude. There are big error bars there. And the microlensing sort of at the unbound side of the spectrum, they have been having some conflicting numbers. So we hope that this is going to get into focus now, especially as more people are coming into the microlensing community. Yeah, but that's a good exercise for a class, I guess.
So maybe I'll take the prerogative here to ask you the last one. What's the next thing that's interesting after TESS? Is it Luar, Habex? What should we start to play?
All of yeah, all of those. But as someone really thinking about orbital mechanics and orbital dynamics. Well, one is of course LSSD, the other one is Plato, thinking about transit surveys, which is a mix of Kepler and TESS. And more recent, I guess, before that happens, Gaia, astrometry of cold Jupiters.
Okay.
Yeah, so we've been doing some work on that too. Hopefully, when we have the time series of Gaia, we're gonna start combining now radial velocities with astrometry and get sort of like a more 3D picture of exoplanets.
Okay, well, if we don't have any other questions, let's thank God we're gonna get